So today we will see the stability of finite slopes. Last class we saw the stability of infinite slopes. We saw different conditions, C soil, Phi soil, C5 soil. Everything was pretty simple. Everything was based on basically our Moore Coulomb envelope and all, right? It was pretty easy to visualize it and derive the expressions for the same. We derive the expressions for factor of safety in terms of stresses, in terms of cohesion, in terms of depth, etc. Right? So today we will see the stability of finite slopes. So we know the basic difference between infinite slopes and finite slopes. We saw that the failure is pretty much translational and rotational in these two. And yeah, we will start with this. So one of the most common method used for slope stability analysis is the Swedish circle method. So I want you to have a pen and paper with you so that you can draw this figure by yourselves and mark these parameters and try to visualize it when we go ahead with the discussion. Okay. So I'll tell you how to draw this figure and then along the way we will derive the same. Okay. So first you just draw this light red line, which is our slope. This line, this ground surface at the base. This is the toe. Toe is A. Then A to B is my slope face. Then BD is my ground surface. Okay. So you can draw the slope first. So draw the slope. And let us see the condition for purely cohesive soil. So first case, it is C alone. Okay, we have only C. There is no phi. Okay, only cohesion. So draw the slope, mark the soil cohesion. Okay, that's it. Right. So this method is called the Swedish circle method. So as you can see, we are trying to subtend the arc of a circle here. Okay. I don't know where this slope is going to fail. I don't know whether it is going to be a toe failure. I don't know whether it is going to be a face failure. I don't know. Okay, that is why I have these light lines here. Can you see these light lines? Can you see this? Yeah. And this is another dark line that I have drawn here. These two light lines also I have drawn here. So I don't know where this slope is going to fail. All right. I don't know. I just don't know. So I have this slope here. I have this face of the slope here. And I know that this soil is cohesive. This is my only information that I have. Okay. So what I'm going to do is I'm going to find out for what weight of this soil wedge this whole condition is going to surpass the equilibrium of the slope. Okay. That is what I'm going to find out. Okay. Let's imagine this particular arc of this circle. Okay. In the Swedish circle method, it assumes that the slip surface is an arc of the circle. Okay. So let me assume that this is my CSF, critical surface of failure, or critical slip circle in this method. Critical slip circle, which is a slip surface along which factor of safety is minimum or it fails. Okay, that is my critical slip circle. So let me imagine this critical slip circle. So everyone can draw this critical slip circle now. So draw this critical slip circle. Hope you are done. Then find out where is the center of that circle. It actually comes somewhere here. Right, it's not exactly at the center, so it comes somewhere here. So you can draw the center, mark the center of that arc of that circle. Then you join this top and the bottom to the center point of that circle. Center point of that circle is O. Okay, so that this distance is R and this distance is R. This is the radius of that circle, of which this critical slip circle is an arc. This arc is a part of that large circle. Okay. So join these 2 points to the center of that circle. That point is O. And so that the distance that is subtended from that point to the toe and to this ground surface points A and D both are equal, R, radius of the circle, right? And also let's say that the angle subtended at the center for that arc of the critical slip circle is theta. Okay. This is my condition. And this AD is that critical slip circle, or that's an arc. The length of that arc is L. Okay, I'm going to assign the parameter L. L is the length of this arc. Okay, this is my condition. Okay, have you marked ABD? Have you drawn the arc and have you marked the center of the circle and radius and theta? Have you marked this? Ready with this much? All right, I think everyone have completed. Okay, now, so imagine there is a vertical line here from the center of the circle. This line, you can see this line. And you also know this soil mass here. All right, this soil mass ABDA. Okay, this is called the wedge soil, soil wedge. I am going to call it the soil wedge. Okay, the weight of that soil wedge is W. Okay, and it acts through its center of gravity, which is at a distance x bar from the center, the vertical line passing through the center of the slip circle. Okay, clear? So W is the weight of this wedge, and it acts at a distance x bar from the vertical line passing through the center of the circle. Clear? So W and x bar also you have to mark now. That's it. So you have marked everything now. So now looking at this figure, you should be able to say what causes this slope failure. What causes slope failure? Gravitational force, right? The force that is going to drag this down, gravitational force due to this soil wedge. Weight of this wedge is going to push this down, correct? And it is going to fail. We are assuming that it is going to fail along the surface AD, correct? Now, what is going to resist it? The shear strength of the soil, right? What is the shear strength of the soil here? Tau is equal to C here. Phi is absent. Phi is 0. So tau is equal to C here, right? So that cohesion is going to act along this surface, right? It is going to act along this surface in this direction I have marked here, and this wedge is trying to move outward and downward, correct? That is the movement that is going to happen, correct? This soil wedge is going to move like this, as you can see my mouse movement. It's going to move like this, right? But the cohesion along this slip surface is going to prevent it from moving like this, right? So this acts in this direction. So what is the total cohesion acting along AD? The length of AD was L, right? So the total cohesion acting along that is L into C, correct? So that L into C is my shear resistance, correct? That's my shear resistance, right? L into C, the total shear resistance, correct? So this much we are clear, everyone? All right. Now let us see. So what are the driving forces here? Driving forces or driving moments here? Driving moment MD is equal to how much? This W into this X, right? That is my driving moment, correct? MD. Considering this as my point of reference, center of that circle. Then resisting moment is how much? CL is the total cohesion that is acting along the surface, right? Into that distance R, right? At any point on this distance is R. So my resisting moment MR is equal to CL into R, and driving moment is equal to W into X, correct? And we know the expression for factor of safety. So factor of safety is equal to driving moments by, sorry, resisting moments by driving moments, right? So resisting moment is CLR, driving moment is WX, right? And L is equal to 2 pi r theta by 360, right? Length of this arc, if that angle subtended is theta and the radius is r, then length of the arc will be L is equal to 2 pi r theta by 360, right? So substituting that here instead of that L, so now my equation changes to CR square theta by WX, correct? So L is equal to 2 pi r theta by 360, C into 2 pi r theta by 360 into R divided by WX. So that will be CR square theta by WX. This is going to be my factor of safety at equilibrium. Sorry, this is my factor of safety. Let us come to equilibrium condition. Okay. So now let us imagine that CM be the mobilized cohesion just before failure, right? So what is this mobilized cohesion? All right, so mobilized cohesion CM. Suppose I think I have explained it with an example in your class. I tried to pull someone towards me, and I asked you to hold yourselves in position, and I tried to pull you towards me, and you mobilized some of your strength and you tried to hold that position. Do you remember? And you will hold that position if I am trying to pull you towards me. Okay, I'm holding you by your hand and I'm trying to pull you towards me, and you are trying to hold your own position, and you mobilize some of your strength to do that. All right, and you have some peak strength, you have some maximum strength. So when the force that I apply surpasses that maximum strength you have, then you start to fail, right? Then you start to move towards me, right? Right? Similarly, so when I'm trying to pull you, you will mobilize some of your strength, right? Similarly, when the soil is trying to fail, it will mobilize some of its cohesion, okay? And at some point, the stresses will be so high that it cannot be resisted by the maximum cohesion the soil have. At that point, what happens? The slope is going to fail, right? So at some point, at any point before failure, the complete cohesion or complete strength of the soil might not have been mobilized, right? But at one point, due to that stresses, at one point, the complete strength of the soil will be mobilized. So Cm will be equal to C. And above that, if you apply more stresses, the forces that you apply cannot be resisted with the C that the soil has, and the slope is going to fail, right? So at some point, your Cm is going to be equal to C when the stresses are very high. When the stresses are high and the cohesion is keeping on getting mobilized, at one point your mobilized cohesion will become equal to cohesion, right? As Yogesh told earlier, at equilibrium Cm will be equal to C, right? So at that case, in that case, your factor of safety will be equal to 1, right? So when your factor of safety is equal to 1, your C will be equal to Cm, and here the equation will be Cm into Lr will be equal to Wx, right? And Cm will be equal to Wx by Lr. And we also know that, factor of safety is equal to C by Cm, right? So basically it is equal to, factor of safety is equal to CLR by Wx, and at equilibrium we know that C is equal to Cm. So in the case of purely cohesive soil, factor of safety with respect to cohesion and the true factor of safety are the same, isn't it? Fc is equal to F in the case of purely cohesive soil. So F is equal to C by Cm, and we know the equation is equal to F is equal to CLR by Wx, right? So my factor of safety in the Swedish circle method is CLR by Wx, and my factor of safety with respect to cohesion is the same as the true cohesion, because the soil doesn't have a parameter of angle of internal friction. Clear? Is that clear? So, right now we assume the surface AD, isn't it? And I got some value of factor of safety here, right? I got some value of factor of safety here. Now what I'm going to do is, I'm going to assume this faded line, okay? I'm going to assume that this is my failure surface. Okay, I'm going to assume that this is my failure surface. Then I will calculate the weight of this wedge. Then again I will go back and calculate my factor of safety. So when I consider this wedge, my length of the arc has reduced, theta has reduced, right? So all those parameters will change, W will change, X bar will change, everything will change, and I will calculate my factor of safety again. Then what I will do, then I will consider this next surface. You can see the next dotted line. I'll consider this. I'll calculate the weight of that wedge. I'll calculate this length of this arc. I'll find out what is that theta. I will go and calculate this factor of safety again. And I will keep on doing that 4 or 5 times probably. And I will find out for which assumed critical slip circle, which assumed slip circle your factor of safety is minimum, or it is going to fail. So you will assume along which of these assumed critical, which of these assumed slip circles has the minimum factor of safety, and that will be your critical slip circle, right? So this is how you do Swedish circle method for calculating the factor of safety against slope failure for a finite slope. Clear? Hope it's clear. But sometimes, as you can see here, sometimes just before the slope fails, there is a possibility for a crack to happen here. When it rains, what happens? This crack will be filled with water, right? Right? Imagine there is a crack in the soil here. Imagine that this is your critical slip circle, okay, AD. Earlier it was extending, this D was on the ground surface, so the critical slip circle was like this, right? It was this much. But now I have observed that there is a tension crack on the soil. The soil here, it has cracked and it has started to move out. Okay, there is a crack here. Okay, and when it rained, suppose when it rains, this gets filled with water. This is my new condition here. All right. Suppose this gets filled with water. Now, the depth of my tension crack is Hc. Okay. Depth of my tension crack is Hc. And when this tension crack comes, what happens? Along this much length, my cohesion is not going to mobilize, isn't it? From the point D to the ground surface, cohesion is not going to mobilize, and that is not going to resist any of this slope movement, right? So the cohesion will only be mobilized along the distance AD, correct? Correct. So previously my arc was theta, D was on the surface, then some crack happened here. So what happens? This line will come and join here, right? D will come here. Correct. That's what happened here. So my L has reduced, my theta has reduced, my theta is theta dash now. So L is equal to R theta dash now, right? So only along this much length only your cohesion is going to mobilize. So CL will be equal to along this length only, right? Now, when it gets filled with water, what happens to the driving force? The driving force further increases, isn't it? As you can see here, the whole weight of this wedge also acts, and the weight of the water inside this crack also acts, right? So these two will act now, isn't it? So this hydrostatic pressure due to the water inside this tension crack also acts along with the weight of the wedge. And as we saw earlier, this theta has reduced to theta dash. So the total length along which the cohesion is mobilized is also decreasing. So now weight of the sliding wedge, it has actually decreased here, as you can see here, right? So weight of the sliding wedge is equal to weight of area bounded by the ground surface, slip circle arc, and the tension crack. The whole thing, weight is the whole thing, but along with that, the hydrostatic pressure due to the water inside this tension crack is also considered now, right? So depth of this tension crack Hc, this depth is 2c by gamma. We will derive that later. All right. So depth of this tension crack Hc is equal to 2c by gamma. And what is this Pw? Pw is my hydrostatic pressure. How much is that? If you look at here, if you look at this point, this depth is Hc, and this is completely filled with water. So if you draw a pressure distribution diagram, what will be the hydrostatic pressure at a depth Hc? Gamma W into Hc. So your pore pressure keeps increasing with depth, isn't it? Right? So if you plot a pressure distribution diagram, you can see that this height is Hc and the base Pw. Pw is equal to gamma W into Hc, right? So you can form a triangle here, right? Pressure distribution diagram. So what will be the total value of this Pw? Area of that triangle. So that will be half into base. Base is how much? Pw is equal to, small pw is equal to Hc into gamma W, and height is Hc. So total capital Pw will be equal to half into Hc gamma W into Hc, right? So my total Pw will be equal to half into gamma W into Hc square, correct? That hydrostatic pressure also acts in driving this wedge down, right? And that distance is y. As you can see here, Pw acts at a distance of y from the surface. So the total moment will be Pw into y. So my factor of safety here will be equal to CLR by Wx plus Pw into y. So this is the effect of tension crack and effect of hydrodynamic pressure or hydrostatic pressure if that tension crack is filled with water. Is that clear? Now that was for cohesive soil, but if the soil is C5 soil, right, cohesive friction soil, then you will go for another method. It is called the method of slices. Okay, it's pretty simple. You just have to divide. You have to assume a slip circle like this, just like what we did earlier. Then what you are going to do is you are going to divide it into different slices. So take a pen and paper and draw this slope surface first. Draw AB. Draw the slope first. Draw the ground surface here. Then B is the head of that slope. Then BA is the face of that slope, and A is the toe of that slope, and again another line here that represents the ground surface. Can you draw? Please draw that. Then I will continue. Hope you are done. Once you have done with the slope and the slip circle, draw the slip circle first. Draw the slip circle, this arc AB. just like what we saw earlier. Just draw that slip circle, and the slip circle is a part of a larger circle of which the center is O. Draw that from that point center O, you draw the radius R and subtend an angle theta. That is subtending an angle theta at the center. Right. Now you can see these pencil marks. This one. All right. Consider these pencil lines, not the red lines. Consider these pencil lines. So you divide it into different slices of thickness b, as you can small b, as you can see here it is marked. So you have to divide it into number of slices having similar thickness b. Okay, so this is the first one, this is the second one, this is the third, fourth, fifth, sixth, seventh, and this is the last one. Okay, draw these lines, these pencil lines you can draw. You can see my mouse movement. Draw these lines. Okay, draw these lines. Okay, the weight of each of these slices, each of these 8 slices, the weight of those will actually act through the center of each of those slices, isn't it? Yes. So let us mark the center, draw that dotted lines at the center of those slices. So you can see here these red lines, the red dashed lines. Okay, you can draw that now. Draw that. So basically in your figure, this line, this dashed line here on the bottom inset photo, as you can see here, the bottom right image, this dashed line represents this dashed line that you are drawing right now. Okay. And we are going to resolve the forces due to that slice now. All right. So what are the forces in that? You can see the inset image here. You can see my mouse movement. So you can see that the weight of that slice acts correct downwards, right? Weight of that, right? Then there is a normal component and there is a tangential component, right? So you have the weight, you have the normal component of the slice, and you have the tangential component of that slice, right? And this normal component is going to act along this center of the circle, right? As you can see here, correct? Can you see this? The normal acts along the center of that circle, and W acts exactly down. It's gravitational force, right? Then I have a tangential component. So here, if you look at this, this might not exactly be the orientation, exactly might not be right. It will be something like this. It will be like this and will be like this. Okay, this is not exactly right, but still, yeah, let's see how it is. Yeah, this is pretty much correct. You can see. So draw the weight of that slice, normal component and tangential component. Draw those components for each of these slices. Draw this dotted line from the center of that circle through the center of each of those slices. You put a dotted line like this, and then from that exactly downward you mark your weight, and along that dotted line, as you can see here, along that dotted line you mark your normal component. So you have your weight and your normal component, then join those two, you have your tangential component. Finish that, then we will continue. All right, now that we have resolved the forces from that wedges, now we can see that what are the forces that is going to drive this slope down. If you look at those, okay, one more thing, throughout this distance till here, you can see that the tangential forces are acting like this in this direction, right, downwards. It is trying to push these down, but here you can see the direction of these tangential forces are opposite, isn't it? Because W is like this and N is like this. It's opposite. So you can see tangential component is acting in this direction, right? Is that clear? So you can resolve those forces for each of these slices. Okay. So finish that, draw that, and mark the directions of the tangential components. So these all will act like this, but once the normal component crosses to the other side of the weight component, then you can see that once you resolve it, the tangential component will be in this direction. Right, as you can see here, there's an arrow here I have marked it. Right. So that angle between that will be same as this theta. As you can see here, this angle will be theta, these angles will be theta. Now, what are the forces that causes the slope to fail here? What causes this slope to fail? This weight of these wedges, obviously weight of this wedge is what is going to cause the slope to fail. But I have resolved that weight into two components now, right? Normal component and tangential component. So which of these components are going to cause the failure of the slope? N alone, T alone, N and T together, which one? T, yeah, because N acts along this center of the circle. It's no effect, right? As you can see here, there is no effect of N, normal component. It acts along this line, right? Normal, it's acting normal to the surface, so no effect, isn't it? But what is going to drive this down, the component of weight, what is going to drive it down is my tangential component, right? So your driving moments here along this surface, the driving moments here will be equal to this T into the radial distance R, right? Correct? So you can see that the driving moment is T into R, and there are so many T's here. So sigma T into R, correct? Sum of all these T tangential components multiplied by that radial distance R, isn't it? That is my driving moment, agree? And what causes the stability of the slope? What resists that movement? As you can see in this figure, this arc length is AB, right? Length of this arc is AB, and I have divided it into different slices, each of length B here, and this length here, arc length here, is delta L. Okay, this distances are delta L. All right. So for each of those slices, the cohesion mobilized for one single slice is how much? C into delta L. Correct? Agree? Total cohesion for each of those slices will be C into delta L. Right? So that C into delta L plus there is also phi in this soil, right? This is a C phi soil. So how much is that phi mobilized? Tan phi is this phi is my angle of internal friction. You can see this equation, resisting force is equal to, what is the basic equation for shear strength of soil? C plus sigma tan phi. Is this equation similar to that? Yes. So C, the total C will be C into delta L plus, what is this N? What is that sigma in that equation? Here N is the normal stresses, right? I have resolved this W into two, normal and tangential, right? So that is normal. So N into tan phi. So total cohesion plus sigma tan phi. This is basically my shear strength equation. So shear strength of the C phi soil is actually resisting this, right? So C delta L plus N into tan phi. So my total resisting moments, this is my resisting force, my total resisting moments will be equal to this into R, right? So R into C into sigma delta L. How much is this sigma delta L? How much is that? Sigma delta L will be delta L plus delta L plus delta L plus delta L plus delta L, like this, the whole thing. So that is my L, that is length of the slip circle, that is AB. That will be equal to 2 pi r theta by 360, same, right? Same as what we saw earlier. So C sigma delta L plus sigma N, total of all these normal forces, into tan phi, the whole thing into radial distance R. That is my resisting moments. So basically my factor of safety equation will be equal to resisting moments divided by driving moments. So it will be R into CL plus sigma n into tan phi by sigma t into R. That R gets cancelled. So this will become my basic equation for factor of safety against failure for C5 soil using the method of slices. Right? Clear? Now imagine, N is my normal stresses here. Imagine there is some water in this soil. Okay, there are pore pressure also in this soil. Okay, so how will this equation change? Okay, my weight component might change. Okay, weight component will change so that my N and T components will change. But how is that going to change in this equation? The normal stress acting along this is going to change because that will become what? Any idea what will become of this N? There is water. I'm talking about the strength mobilized in the soil alone, isn't it? So this component, you have to subtract your pore pressure from this. So the equation will become this N minus U, isn't it? Yes or no? So it will be CL plus sigma N minus U into tan phi by sigma T. Well, then again, your C and phi also can change to effective or true cohesion and true angle of internal friction. So it may be C dash and phi dash. So here in this equation it is C and phi because we are considered it is dry soil, so it is C and phi itself. But if you are calculating the strength parameters of that wet soil, then you have to calculate your C dash and phi dash, your true cohesion and true angle of internal friction instead of your apparent C and phi, isn't it? So basically this equation is going to change as F is equal to CL plus sigma bracket open N minus U bracket close tan phi divided by sigma T, because you are considering the resisting forces due to the soil alone, isn't it? So your normal forces is actually going to reduce. The normal stresses that's going to act on the soil alone is actually going to reduce because some of that will be taken by pore water, right? So this equation will become CL plus sigma N minus U into tan phi by sigma T. Clear? Hope it's clear. All right. I think we'll stop for now.